All right, welcome. Any last minute questions for the exam tomorrow? I've only had one person say they want to take the exam remotely. So if you haven't reached out, you want to do that ASAP because I can't guarantee if I don't get it soon that I'll be able to get it all set up. It's always better for you to come to the class. That way you can answer, I can answer questions, but if you need to do it remotely, that's perfectly fine. We've got a mechanism to set that up. So we'll make it work. But any questions on homework or concepts or any of the stuff we did in class on the review on Tuesday?
I had a question about like the power analysis.
Yep. The power analysis, like say more, like the dissipation and.
Yeah, it's a.
All right, let's see if we can find. I gotta go up one. Ooh. Okay, let's see if this has an example. It's always good to start with something. And let's see. Let's see if chapter 3 has anything. I don't know, so, well, we can always find one if there's a couple of power supplies in it. Let's see. I don't know if I want to do that one. Want to do number 440? See if it is, I think it will be that it's one's going to be a source and one's going to be a load. I'm not certain of that, but I think that that's the case. I'm going to try that one. All right. And let's just do this problem. I don't know what the problem actually asks for, but let's go ahead and do this problem and try to figure out like what would be the power dissipated or absorbed by all the elements in the circuit. Okay, that reasonable? And I'll let you pick which method do you want to use? Do you want to use mesh? Do you want to use nodal? I don't have any preference. I'll let you pick. Mesh? Everybody want to do mesh? We can do mesh. You can do nodal analysis on this one as well, right? Because even though you have voltage sources, you don't have any voltage sources that are going to mess up your results. But we can certainly do mesh. I would probably do this node here and that node here. Only because, I mean, I could combine the 5 and the 2 ohm resistor to be able to do that, but I probably wouldn't just because I might need to know like what that voltage is to calculate what the 2 ohm resistor, the power the 2 ohm resistor dissipates. So once I start doing a lot of stuff, it's not worth it to me to combine elements. So I just go ahead and analyze it. We can do both. Well, let's do this. We'll do mesh first and then we'll do nodal. And you get the best of both worlds. How's that? All right, so we'll start off with mesh. Here's I1. Here's I2. Step 1, right? Pick the mesh currents and assumed current directions. Step 2 is apply a voltage drops in the direction of the current flow. So we see that we have plus to minus here and plus to minus here. That's for the I1 loop. We're going to do the same thing for I2. Plus to minus here, plus to minus here, and plus to minus here. We didn't do that for the voltage sources because we know what those voltages are. So we don't have to assume or anything. We actually just go ahead and write it down. So now we can actually start writing equations. So negative 50, because that's a voltage rise, plus 4I1, plus 2I2, plus 2I2, 2I1, minus 2I2 is going to be equal to 0. That's our first equation. Our second equation, and again, I'm just picking the lower left-hand sort of place to start just for consistency, so that way I don't forget anything. You can start wherever you want. You just want to make sure you close the loop. So I always start in the lower left-hand corner, but you don't have to. That's just how I was taught, and that's what I've been doing for many years. So we have 2I2 minus 2I1 plus 5I2 plus 2I2. And in the direction of current, the 20 volts is increasing. So that's a negative 20. And that's going to be equal to 0. Okay. I'm going to solve and set up in the equations. This is 50 and this is 20. That's going to be equal to 6I1 minus 2I2 minus 2I1, and I've got 2, 7 plus 9 I2. So in my matrix setup, I have 50, 20 equals 6, negative 2, negative 2, and 9 times I1 and I2. So I1 and I2 are going to be equal to 6 minus 2 minus 2, 9, raised to the negative 1 times 50 and 20. Okay, I've got to enter these into MATLAB because I actually asked you to calculate power dissipated and all that stuff, or power absorbed. So let's go ahead and actually calculate what I1 and I2 are going to be. And then once we have that, then we should be able to figure out, what is happening in terms of power dissipation and power absorbed. So this is thinking. Everybody have MATLAB installed on their computers or still holding out? You have what? Yeah, you're more than welcome to use whatever tool you're most comfortable with, for sure. Like I said, for MATLAB, for me, you can actually see my work on the board. So I'm not hiding anything in a calculator. In case I type something in, you can actually see the results there. If MATLAB ever launched it. I did just upgrade. It was a big Windows update this last time, right? It took like 30 minutes or 45 minutes to actually restart, so, and be ready. So hopefully that didn't kill anything in MATLAB land. All right. So I have an R matrix. Oh, I thought it was ready. I guess not. And that's going to be equal to, this is really annoying. I wish that it wouldn't ask me to do this. So I have 6 minus 2 minus 2 and 9. 6 minus 2, minus 2, and 9. And I'll enter that in so you can see that that's our R matrix. My voltage matrix is equal to 50 and 20. So my current matrix is equal to the inverse of R times my voltage. And I get 9.8 and 4.4 amps. So going back over here, I get 9.8 and 4.4 amps in that direction. So now I'm just going to start listing out P absorbed or P delivered. So P of my 50 volt source, that's going to be equal to 50 times 9.8. Now, the only question we need to do is it supplying or absorbing power? Supplying, because, keep going. In the direction of current flow, the voltage is increasing. The only way you can get a higher voltage is if you're putting power into the system. So this is, we'll just use the term S to say that it's supplying. Now we'll go P4 ohm. And P4 ohm, the way to get it is I squared R, probably the fastest way to get it. And that is absorbing. So you don't even have to think about a resistor, whether it's supplying or absorbing. You know it has to absorb because it doesn't have the ability to store any energy to be able to dump it out. Then we're going to go to, we'll call this P2A. That's our 2 ohm resistor, our first resistor. So again, that's going to be I squared R. Which I do I use? Do I use the 9.8 or the 4.4? So technically I use both, right? So it's going to be 9.8 minus 4.4, that quantity squared, times my 2 ohm resistor. And that again is absorbing. And here's the thing. It doesn't matter if it's going in the up or down direction with current, it's still absorbing power. Now I'll do my P5 ohm. So that's just going to be I squared R. There's only one current flowing through there. 4.4 squared times 5, absorbing. My P2B, which is my second 2 ohm resistor. I've only got one current flow in there, times 2. And then lastly, my P20 volt. We know there's a current of 4.4. Oh, I squared it. I shouldn't have squared it. So that's 4.4 V times I, or 4.4 times 20, so it's really I times V. Is it supplying or absorbing? Supplying, because in the direction of current, the voltage is increased. That's how you would do it with mesh. Let's do it with nodal. We'll call that V1 and V2. So we'll do the V1 node first. So we're going to assume current directions like that. And again, we don't know if those are right or wrong, but it doesn't matter to us. So current into the node is 50 minus V1 divided by 4. And then the two other currents are out of the node. So that's going to be equal to V1 over 2 plus V1 minus V2 over 5. That's our first node equation. Our second one is going to be current into the node. So that is V1 minus V2 over 5. And this is what I think is really good about using current into the node equals current out of the node. If I know that positive current flow is from a higher potential to a lower potential, or plus to minus, you can see that this V1 minus V2 over 5 is essentially the same thing as it is over here. But because I moved it to the other side of the equation, that takes into account the fact that I'm basically swapping directions. So I don't have to put negatives. Like some people say, well, make it V2 minus V1 over 5. But I don't like doing that because I think you're kind of cheating the system. All you're doing is saying it's going in or it's going out of the node. So very, very simple. You don't have to overanalyze it. So V1 minus V2 over 5. And then that's current into the node. The current out of the node is V2. Now, what is this voltage here? Minus 20. It's a minus 20 volts, right? Because from here to here, this is at a minus 20 volts, isn't it? Relative to reference. So don't just put minus 20, make sure you understand polarities. And is it minus 20 or minus a minus 20? And that gets divided by 2. So now I can go ahead and clean all these up. So I've got 50 over 4, which is 12.5, I believe, is going to be equal to V1 times 1/4 plus 1/2 plus 1/5 minus V2 over 5. And my other equation, I have, let's see, negative 10 is going to be equal to negative V1 over 5 plus V2 times 1 over 5 plus 1 over 2. So entering those into my matrices, I have 12.5 minus 10. That's going to equal, I guess I could do common denominator. So let's see. So that's 5, 10, 15. So I think that's 19 over 20, if I did that correctly. Minus 1/5, minus 1/5. And this is 7 over 10 times V1 and V2. Okay. Everybody see that? Okay, so now to do my P delivered, P absorbed, I've got to do a little bit of additional work, right? Because I don't know what the current through the 50 volt is, and I don't know what the current is here. So how would I go ahead and solve for that? Well, I could also say it's P50, which is going to be equal to 50 volts times, and I'm going to put these in parentheses because I'm going to have 50 minus V1 divided by 4, right? That's V times I. So the current there takes a little more work. I actually have to figure out what the current is. Yep. So I'm trying to solve for the current out of that 50 volt source. So I'm taking this voltage here, subtracting that voltage, and dividing by the 4 ohm resistor. So I did 50, which is the voltage in the lower point. Then I subtracted the V1 voltage, and I divided that by 4. That's how I get the current. Okay. Now do you want me to do all of these, or do you want me to just do a few of them? Let me do the next one. Let's do the next one for the resistor, and let's show how I would do the P4 ohm. So the way that I would do the P4 ohm is I would just do V squared over R. Here's where you got to be careful. The V we're talking about is the voltage drop across the 4 ohm resistor. It is not 50 volts and it is not V1. So it is 50 minus V1 squared over 4. Okay. So that's V squared over R. It looks similar to this equation over here, but it actually is not the same equation, is it? It is a different equation. Everybody see how I got that current? Anybody not see it? Oh. Okay, hold on, let me see. Thanks, Arthur. Just let me know if you're talking. Sometimes I can't tell. So how did I get that? Let's write it out. So what I'm looking for is V squared over R. Do you agree with that? So I need V 4 ohm, or we'll call it V 4 ohm in this case. How do I get the voltage drop across the 4 ohm resistor? I take this voltage here and I subtract that voltage. So V4 is going to be equal to 50. And the other terminal is V1.
I was just having trouble realizing.
Oh, yeah. So it's V squared over R. Do you need to see any more of these calculated out, or? Because that's the only way that I would do those. And because you have every node voltage, right? You know this voltage, that voltage, that voltage, that voltage, you should be able to do V squared over R. The only one that might be a little bit confusing is here, right? So over here, if I'm going to get what the power is, that's going to be equal to V times I, it's 20 volts, multiplied by V2 minus a minus 20 all over 2 ohms. And the nice thing about doing the nodal analysis, like this one, you know for sure it's going to be a positive number. Over here, it could be a negative number, couldn't it? It's possible it could be a negative number. So what you'd have to do is you plug in your value of V1. If it's greater than 50 volts, then you know that it's actually absorbing power, right? Because you have 50 minus a number that's greater than 50 is going to give you a negative number, and 50 times a negative number is a negative number. So that would be a negative power, which means it's not supplying power, it's actually absorbing power, which hopefully makes sense, because the only way I get current flow through here is if V1 is greater than 50 volts, right? That answer your question, Luke, or did I confuse you even more? Anybody else? More confused? It got really quiet, so that always makes me nervous, like people are more confused. Are you all more confused? What's that? Okay. Anybody else agree with Homa and Luke that it makes more sense, or now you're more like, oh boy? Because all it is just applying the exact same stuff that we've been doing and setting it up into some way that you can solve for it. So this one, you might be better off to do mesh analysis because it actually gives you those currents pretty quickly. But if you did it with nodal analysis, because you chose a different way, it's not that much effort to figure out what the currents are, in my opinion. So go from there. All right, any other last minute test questions?
Yeah.
How about we do the same problem, but we'll do a Thevenin? There's a bunch of different ways to do this one, right? So the Thevenin equivalent, I'm looking for VA to B. So to solve for VA to B, I already solved these currents, but had I actually used nodal analysis, I would have immediately gotten what V2 is, right? And V2 is the Thevenin equivalent voltage. So in some cases, it makes no sense to do mesh analysis. In other cases, it's better to do nodal analysis, like solving for voltages makes sense. So let's go back up over here, and we're gonna plug in this equation here, and we're gonna solve for V1 and V2. So my Y matrix, or my G matrix, which is the inverse of my resistance, 19 over 20. Oops. Minus 1/5. I think it was minus 1/5 and 7/10. That's my G matrix, my conductance matrix. Okay. Now I've got to go ahead and solve for my current matrix, because over here, these are actually currents, are they not? They're not voltages, they're currents. So I have 12.5 and minus 10. And so now my V matrix is going to be equal to the inverse of G times my I matrix. So I get 10.8 and negative 11.2. So that's negative 11.2 volts. That is V Thevenin. To solve for the Thevenin equivalent impedance, you certainly could put a short circuit over here and then redo your work. But I mean, go ahead and solve for the current, but that might be a lot of work to do that. All I would do is turn off these supplies because they're independent, right? And replace them with their internal equivalent input impedances. 4, 2, 5, 2, and then I do a bunch of series parallel combinations. So what I see, 4 in parallel with 2 plus 5, all that's in parallel with 2. So product over sum, we have 8 over 6 plus 30 over 6. It's 38 over 6. You all agree with that? That's in parallel with 2. So let's see. So that's product over sum. So that's going to be equal to 12 over 6 all over 38 over 6 plus 12 over 6. So this is where I taught my son, and it took me a minute, but I'm going to factor out things quite a bit. So I can see that that's going to be equal to 6 and 2. 6 and 1, sorry. And let's see, 38 divided by 2 is 19. And that becomes 3. So 19 times 6 is 104 over 3, all over 50 over 6. I invert and multiply, and I have 104 over 3 times 6 over, over 50. I can see that those cancel out, and then I can divide this by 2. So I get 25 and 52. So that becomes 104. Sorry about that. 104 divided by 25. So my Thevenin equivalent is minus to plus 11.2. And in series with that, I have a 104 divided by 25 ohm resistor. Oh. Catch back up, or? So that's how you do this one. That makes sense? That makes sense?
Finding the equilibrium distance.
Yep.
I took something about putting it short with the terminals.
Yeah, so I wasn't gonna actually find the R equivalent there. I was gonna find I Norton, right, by shorting out the terminals. And then I could go ahead and solve for R equivalent by saying V Thevenin divided by I Norton. So instead of doing that here, I just said, you know what, I'll just do the easy way. I don't have any dependent sources, so usually, not always, but usually it's easier to do it that way.
So if you have dependent source, you would have. So
I either will do I Norton V Thevenin, or I will apply a test voltage, a 1 volt test source, and then solve with a current coming out of it. Either one of those will work. But it's only for dependent sources because remember, there's no way to turn off dependent sources. So you can't find a resistance when something has a voltage in or a current in it. So that's why you're forced to do it that way. Any other questions?
General question.
Yes.
I know you said that oil.
Boylstad?
Yeah, has some good examples. Do you have like old exams or
I don't have any old exams or reviews other than the one because the way that I teach this class, it just depends on how the class goes. And so a lot of it is based on just look at the homework. And if you can understand the homework, you do it that way. The thing about doing old exams is always a bad idea because it just means you just study that material and you think you know it, but you actually don't. And because this is such an important class in terms of getting a fundamental understanding, it's usually much better to just go ahead and just understand how to do the homework. And then we just answer, do whatever problems and go from there. Okay.
So would you suggest like going back to the homework and like trying to problems again?
I would go through the homework and make sure you don't have to redo the problems. Just see if you can actually come up with an approach, like kind of do it really quickly. Like, can I go ahead and tackle this problem? And so that you have to be disciplined enough to say, yes, I'm actually going back and redoing this, or I'm just looking at, the homework answers and just going through it really quickly. So it really depends on you. If you can't stay disciplined, then you might as well say, yes, I'll just tackle the problem from scratch. But the Showham's outline stuff, that's even better than Boylstad. First off, it's a lot cheaper. And the Boylstad book is not intended to be a quick reference for this class. That's actually a class, and I don't know what they use at SMCC, if they use the Boylstad book for circuits or not, but that's actually like explaining the material. So it's like a 500 or 600 page book with a lot of detail, and a lot of explanation. Where the circuit analysis stuff, the Showham's outline series is like, you do KVL and KCL, and they just kind of throw a few topics on there very succinctly, and then start showing you problems. So that whole Showham's outline series is probably 200 pages, but they've got 80 problems or something like that per section. So it's a very different way of looking at it. So for this class, I really like the Showham's one much better. Okay, anything else? Yes, sir.
So when we're solving like the equations for total or KVL, KCL, it's very well possible to have like do like I1, I2, I3, and then BX. Like at the end, if you need to find it for some reason.
Yeah.
Okay.
You can stuff inside your matrix anything you want.
And that blows my mind and all like that.
Yeah. No, because you're writing a bunch of equations, right? If you have 10 equations or 10 unknowns, you need 10 equations. So you can put that in a matrix and invert it, and you can get the results you need. You just have to make sure that each equation has those 10 variables in it. So that's why we went back and said it's 0 Vx or whatever on all the equations. But yeah, you can keep adding equations as much as you want. It's a good and a bad thing about matrices. It's good because you can get all the information that you want, but it's bad because the matrices can be get very quickly unruly. So when we did this problem here, you remember how we went back and calculated these powers by doing the calculations? There was nothing preventing us from saying that I4 is equal to 50 minus V1 divided by 4. And we could have stuffed that into the matrix over here. Then we would have had a 3 by 3. So we certainly could have done that, but it may not necessarily be, it might be that it's more work. So at some point you have to decide, is it more work to do it this way? Or is it just easier to go ahead and do something that's more efficient? That's all. So that's the good thing about circuit analysis, right? You have all these tools, you get to decide which ones you want to use. And part of that could be you're more comfortable. Like you all said, you want to do mesh analysis on this first problem, which is perfectly fine. It's just, there are easier methods, in my opinion, to solve some of the real world circuit analysis problems that you'll be doing, but it doesn't make sense for you to use nodal analysis if you're really not confident in using it. So you use it as much as you feel comfortable with. But it's also like, anybody here play sports a little bit? How do you get better at something? You keep practicing, right? Well, what if you're a basketball player and you got to learn how to use your left hand if you're right-handed, right? Be able to put up layups or something like that. Do you just keep shooting right-handed? Or do you like, I hate shooting with my left, but I'm going to put my hand up on my left and just keep practicing. It's going to look awful and I'm going to miss all kinds of bunny layups because I'm not confident with my left hand. But eventually, over time, it'll be almost as good as your dominant hand. So the suggestion there is you practice with something that feels uncomfortable and awkward, and then eventually it doesn't feel uncomfortable or awkward. It feels second nature. It feels really easy. I use that example because my son's been practicing basketball pretty steadily for about 2 years. And from day one, when he was doing left-handed layups, I was telling him, you've got to practice with your left. You've got to practice with your left. And so when he was doing practices, his teammates were getting more layups than him because he was, putting up with his left hand. But the coach was, he'd always tell my son, good left, good left, good left. And so now he's at the point where he's very comfortable with his left. And so when he's putting layups up, he doesn't get stuck on his left hand nearly as much as those other kids do because he's going. And so it's paid itself off now. So it's hard, right? You all want the glory. You all want that. Do the easy part. But at some point you switch to the hard part. And that's just how to live life, I guess. Try to do the hard stuff. Don't always do the easy stuff. I got up this morning at 4:45 to go for a run. I actually ran in my basement. It was not nice, but I did not want to run in my basement. That was so boring because I don't have a TV in there. It's awful. It was 35 degrees or something like that at my house when I got up at that hour. And it's dark. I mean, it's pitch dark. I don't mind running in the dark, but running in the cold. But the point is I had to get my butt out of bed, even though I want to stay warm, and just start moving my body. So don't do easy, because you'll find out the rest of life is much harder when you take the easy way out in all cases. Anyway, I'll get off my pulpit here. Anything else?
Can you like a Norton one for the staff?
Norton, when we did nodal analysis, this problem right here, this was Norton, wasn't it? Oh, Norton equivalent circuit. Do you want to just do this problem with just doing Norton? Okay. The equivalent circuit stuff is all the same, isn't it? So that doesn't change. So to do the Norton equivalent, I'm going to short that out and solve for I. We'll call it AB, but it really doesn't exist there. But for all intents and purposes, we'll call it IAB. Now, how should we solve for IAB? We can't just throw those in the trash because they're short-circuited, right? And the reason why we can't throw those in the trash is because you got a power supply here, which is going to contribute some current that can go in there.
If that power supply wasn't there, we just design that for it.
Yeah, because how much current would go through here if it's shorted out? I'll redo that. How much current goes here?
No.
Yeah, if you're not sure, let's do the series parallel combination, right? So R is going to be equal to product over sum. What's the resistance of a short circuit? 2 times 0 over 2 plus 0 is equal to 0, right? So no current goes through the 2 ohm resistor because there's a nice path that has 0 resistance to go through. So if you didn't have that power supply there, you can take that 2 ohm resistor and completely exit out because it doesn't have any contribution whatsoever. Okay? But what we'll do is we'll actually do this again here. Now we'll put our short circuit. And we'll solve for IN. And this is where we have to be careful. If we were to do nodal analysis over here, right, we really are setting ourselves up for danger because we know that that voltage would in fact be equal to 0, right? So it can complicate things a little bit when we're just trying to look for, using nodal analysis for short circuits. We could certainly, we could solve for the node voltage here and maybe, well, we don't even need to do it here, but we only have that one nodal equation, right? So it can be a little bit fussy. I mean, we can see that we've got a current here, here, and here, but all that current is going to go down through there, right? Then we would have to do another one to figure out what the current flow through this would be, right? So that's why you got to be very careful about using nodal analysis because it tricks you into forgetting about this node there or that loop, that current contribution from that source. So if you wanted to do nodal analysis, the best way to do it is to treat that as 2 circuits, almost using superposition, right? So this is my first circuit, and that is IN. And then I do my second circuit. And then the 2 currents summed together is the actual IN. So you certainly could do that. But I think most of you all would forget about doing this last part, right? Most likely. So let's just go ahead and do mesh analysis here. So I've got 3 nodes, or 3 meshes, I'm sorry. So I've got -50 plus 4I1 plus 2I1 minus 2I2 equals 0. Next one, I have -2I1 plus 2I2 plus 5I2 plus 2I2 minus 2I3. And this is minus to plus. So in the direction of current, I see that that's an increase in voltage. So that becomes minus 20. That's going to be equal to 0. My last loop now going in the other direction, this is an actual voltage drop. So that becomes a positive 20, not a negative 20. And that becomes plus 2I3 minus 2I2, and that sums to 0. So my 3 currents, or rewriting my equation, I have 50 equals 6I1 minus 2I2, and I've got 0I3 because I have 3 equations and I have 3 unknowns. I'm going to go ahead and start filling in the fact that I want to make my matrices square. And then this becomes 20 equals minus 2I1, and I have 9I2 minus 2I3. And my last equation is -20 equals 0I1 minus 2I2 and plus 2I3. And if you wanted to, you could be lazy and you could add another equation and say IN equals I3, but I don't think we should stuff that into our matrix. So now 50, 20 minus 20 equals 6 minus 2, 0, minus 2, 9, minus 2, 0, minus 2, 2 times I1, I2, and I3. So you would solve for I3, or we can even call that IN. Anybody need to see that entered in, or? So you just put a short circuit to solve for IN. If you don't like doing that, you can solve for V Thevenin and R equivalent, and then you know that I Norton is equal to V Thevenin divided by R equivalent, right? Like that's another way to do it. So it might be good to check your work. If you're doing an exam or homework and you want to check your work, you can just compare the two and see if you get the same result. Okay? Anything else? So if you have a Norton or a Thevenin with a dependent source, you can't solve for R equivalent. So at that point, you have to do both V Thevenin and I Norton to solve for those. I don't know if I have one. Let's see. There's one right here, 445, figure 445. Want to do that one?
Yeah.
They're going to help you study? Does it help you at all? Maybe, maybe not. I don't know.
That's it, bro.
Okay. So this is a dependent system. So we got to solve for V Thevenin and I Norton, or we have to solve for V Thevenin and then solve for I test given a V test. Right? Either one of those will work, but you still have to solve for either V Thevenin and I Norton. You know what I mean? You have to solve for either V Thevenin or I Norton no matter what, because the Thevenin or Norton equivalent means you need to solve for that. So let's go ahead and solve for V Thevenin. So I'm just going to ignore that and just put that, get rid of that dash line. And what I might do is, let's see. Yeah, I'll probably just do a loop equation here because I've got a couple nodes in there. I don't want to complicate it. So I'm going to do, starting over here, -4 times I, and that current here is IX. So let's just call it IX. Minus to plus, that's not negative, that's positive, sorry. Minus to plus is -6IX plus 6IX. And then minus to plus, -20 equals 0. So what I see is these two will cancel out, and I've got 4IX equals 20. So IX equals 5, and V Thevenin equals 6 times 5, or 30 volts. Okay? Let's do the test one on this case. Let's actually do the test source and then see what we end up with. So we have 4, 20, minus to plus 6, and then I'm going to put just a 1 volt source here. And that was 6IX. Okay, so again, I'll probably just do mesh because I have a bunch of nodes over here. So now I got to be careful because this is I1 and this is I2. So in the first case, I1 was equal to IX. That's not the case anymore. So I have 4I1 minus 6IX plus 6I1 minus 6I2, and then minus 20 equals 0. Now I do my next loop. I've got 6I2 minus 6I1, and this is plus to minus here. So that becomes plus 1, and that's going to equal 0. Okay? And I can see that once I know what I2 is, then that gives me what the current is from the test source. So then I can use that to actually find my R equivalent. So I've got, let's see, I've got 20 and -1 equals, I've got, this is, let's see, so I have, oh, I'm going to have 3 equations because I see I have that IX variable. So I got to add my IX to the dependent source. That's going to be equal to I1 minus I2. So my 3 equations, right? Let's see. So I've got my first equation. I'll do this as my first, second, and third equation. So I've got 10 I1 minus 6 I2 minus 6 times IX is my first equation. My second equation, I've got minus 6 I1, positive 6 I2, and 0 times IX. And over here I have I1 minus I2 and minus IX. I got a little bit crazy. I realize it kind of halfway, but I included my variables in here. So technically I should erase all of these variables. So this becomes 1 minus 1 minus 1. And then these numbers just kind of disappear. Now, my R equivalent is equal to V Thevenin, oh, sorry, not V Thevenin, V test divided by I2, or 1 volt over I2. And that's how you would do it if you have a dependent source.
So how come the test source doesn't introduce any extra current?
It does.
It does.
Yeah. But why do I care? I'm looking for an equivalent resistance as seen by the outside world. So if I have a 1 volt resistor and it's drawing out current, it actually, that's the resistance, right? That's the equivalent resistance seen by the outside world. That actually isn't used to calculate V Thevenin or I Norton, is it? I didn't put that 1 volt source in until I was calculating my R equivalent. So I didn't put it in there to solve for V Thevenin or I Norton. I just did it to solve for the equivalent current, the equivalent resistance. Okay. Anything else? All right, well, let's finish up. Let's at least finish up this. We only have 5 slides to go, and maybe I'll let you out a tiny bit early. No? Did anybody? Oh, why isn't this working? So did anybody go ahead and prove how capacitors in series add as resistors, inductors? Well, conceptually, if I have a capacitor and another capacitor like this, right? What is a capacitor essentially? It's 2 metallic plates or metal plates separated by a dielectric. I haven't increased the amount of area that I have on these plates to put electrons, right? Because the electrons are trying to get across to that dielectric. All I've done is taking my capacitors that look like this and basically done this. I haven't allowed more area to put charge on, but I've increased the distance or the insulation between those two, which means they have a weaker polarity there, right? There's a lower attraction to there because it's harder to get to. So effectively, I'm reducing the capacitance. I'm making it harder for that device to store energy. How does that work here? Well, remember, this is C dV dt. That's the current. or the voltage is 1 over C integral of I, right? So if I want to just do two capacitors here, C1 and C2, and solve for the equivalency, what I need to do is a KVL loop. So I know that negative Vs plus 1 over C1 integral of I plus 1 over C integral of I has got to equal 0 because that's my KVL equation. I can use that to simplify my life because the current I through here is the same current through C1 and C2. So I can factor out the integral of I, 1 over C1 plus 1 over C2 times the integral of I is going to be equal to Vs. And the definition of an equivalent capacitor here is Vs is going to be equal to 1 over C equivalent times the integral of I. Equating these two terms together means 1 over C equivalent is equal to 1 over C1 plus 1 over C2. So when I invert the C equivalent, or the 1 over C equivalent, I got 1 over C1 plus 1 over C2, all that inverted. So capacitors in series add just like resistors do in parallel. So that's the actual derivation to do that. How about to do it in parallel? Well, now we're just doing voltages. So V equals C dV dt. And we'll just do two capacitors, right? So the source current, the current in is equal to the currents out. So that's C1 dV dt plus C2 dV dt. Since the voltage across C1 and C2 are the same, we can factor out the dV dt. And same thing over here, IS equals C equivalent dV dt. So that tells me that C equivalent is equal to C1 plus C2. So capacitors in parallel add just like resistors in series, which again makes sense because if I have a capacitor here with a plate and insulation and I put another one over here, effectively all I've done, and I'm blowing up the scale a little bit, but I haven't increased the insulation resistance. I just have more area to store electrons on and put actual electrons there so I can actually get, the results I'm looking for. Okay? Questions on that? So we've already done capacitors, last two classes, the class that we actually had class, we did inductors, and this is when you can do product over sum. Right, but it applies to two and only two resistors or capacitors or inductors in parallel. In series. Right? Okay. All right, so can you simplify this circuit down? Yeah. Let's start off with this one. Those are in parallel. So let's go ahead and copy this to whiteboard. And we'll check our answer at the end. All right, so the first thing we're going to do is we're going to combine those two inductors into one. So that's product over sum. So product 6 over 5. This is 0.8. This is 1 microfarad. Now, two capacitors in a series add like they would be in parallel, like resistors in parallel. So that's product over sum, 18 over 9, which is equal to 2. That's my first combination. Now, I'm going to combine these two, which are in parallel with each other. And capacitors in parallel add just like resistors in series. So that's going to be equal to 3 microfarad. and this is 1.2. And since the capacitor and the inductors can't be added together, I'm going to go ahead and move those around. All I'm looking for is equivalency over here. I'm not saying what's happening inside the circuit is exactly the same, but I'm going to move them around so that I can add them together. And what I'm left with is 2 Henry and whoops. 3 microfarad capacitor in the series. Those would be the equivalents. Let's check our work. Looks about the same to me. Again, I'm just showing what the equivalency is looking externally, not internally, because once I move those inductors around, then I've changed the voltage drops, right? So I'm not saying the individual voltage drops are going to be correct. I'm just saying as an aggregate, looking at it externally, you'll end up with, you know, something that looks equivalent. Remember op amp integrators or op amps? The whole thing about op amps, 2 sort of key things, right? The input impedance is equal to infinity, and the open loop gain is equal to infinity, right? Those are the 2 key things. And when we do that, we know that this current I has to go over there, right? First thing. And the second thing is this open loop gain is really, really big, which means that the voltage difference between these two had better be small, really small. Because if it's anything big, your op amp's going to saturate, you won't get good results. So we say the plus to minus voltage drop across here is 0 in an ideal op amp. So all the current goes through here, and my current I solve for it, Vs minus the other side of the resistor is 0, right? Because it's ground. There's no voltage difference between these two. So this is at 0 volts, which means that's at 0 volts. And then I divide that by R1 is my current in. Then my current through my capacitor, right? The current there is, let's see, so I equals C dV dt. So that equals that same current there. So that current is this current that goes through in this direction, right? Everybody understand that? Now, the hard part about that is, well, how do I go ahead and solve for what my output voltage is? So I know what the current is, but I don't know what the output voltage is. Well, the output voltage I can find over here is going to be this voltage plus to minus the voltage over there. So the voltage across the feedback capacitor is 1 over C integral of I of t dt. So this here is Vs over R in or R1. This output, and I also should say it's negative, right? Because it goes from a higher potential to a lower potential. So this has to be a negative output here. So if I put that in here, my output voltage is going to be equal to -1 over C integral of my input voltage divided by R1 dt. And so now I move out my R1, so V out is equal to -1 over RC integral of V1 dt. And this goes all the way from minus infinity to any time. If I want to start at t equals 0, I have to include the initial condition. So this type of device is an analog integrator. It integrates the input voltage, doesn't it? It integrates V. So that's an op amp integrator. The open loop gain. So an op amp, if you look at an ideal op amp, How an ideal op amp works is there's no current that can go into the op amp in either terminal because it has an infinite internal impedance. The other thing is an open loop V out is going to be equal to V plus minus V minus times the open loop gain. Okay. An ideal op amp has infinity for an open loop gain. It rocks the voltage up to very, very high values. So because of that, if I want that to not saturate, this voltage had better be equal to 0 to make sure that I don't oversaturate my op amp. Okay. So the ideal op amp has infinite internal impedance and infinite open loop gain. In the real world, op amps have greater than 1 mega ohm of internal impedance or equivalent internal impedance, and the gains are like 200K, 500,000, really big numbers. So we approximate real world op amps using ideal conditions just to make the work a little easier to understand. Okay. Sure. A differentiator is going to be very similar. The difference is that now what I'm doing over here is the current through here, IC1 or IN is equal to C dV/dt. And my output voltage, V out, is equal to negative RF times I. So my output voltage is negative RF times C dV/dt. So this differentiates the input. And it wasn't that long ago that that's how you used to model systems. They used to do these things called analog computers, which had a bunch of op amps, and they were special op amps, but they would make these circuits and they would connect things in different configurations to simulate a physical system. Because a physical system, we'll learn, is just a bunch of differential equations that you solve or you have to figure out how to solve, and then you just inject signals to it to see how the system responds. So probably mid-80s, that's how you would analyze sort of complicated systems because you didn't have the horsepower and computers to be able to do it. Now, analog computers have gone away of the dodo bird. They don't exist because computers, you can do it just like the slide rule. Like I'm 55 and I never used a slide rule. But had you gone 10 years to college earlier, you would have been using slide rules because to buy a desktop calculator, like one of those would have been $5,000 back in the late 70s. But now you bought them for what, 30 bucks, 40 bucks for your TIs. So yeah, you don't see them anymore, but they're still really good because they help us get a pretty good understanding of how to solve and write differential equations, which we'll be moving into in the next class.
You know how to use the slide rule?
I could probably figure it out because my math is reasonably good, but yeah, no, I would not be able to use a slide rule very efficiently. It would take me some time. But it worked really well. And once you got good at it, it's just like people with an abacus. You could do it so fast that you didn't even have to think about it. No, it wouldn't be at all because nobody uses them.
Master of arcane technology.
Yeah,
Just
if you could,
that right there.
if you could say you could use like, the way you used to program computers, you use punch cards. If people said, yeah, I'm a master at putting, doing punch cards, they'd look at you like, why would I hire you? That's 50+ year technology. And when I started the university, that was in 88, they still had a computer over there that did accept punch cards. It was probably just like on the wall. But, that wasn't that long ago. Like you all have smartphones that could do this, but prior to, having Windows and all that stuff, to get access to information was not easy. You had to really know, you had to be pretty efficient at computers. And I remember buying a 4 meg RAM chip for $100. Now I don't even think that exists. I don't think you can buy a PC with less than a gig of RAM. So sometimes improvements are better, right? All right, Arthur has a question or comment? Oh yeah, washers and dryers use punch cards. That might be a little different than I'm thinking about programming. That might have just been like a special key to figure out, okay, this you're open, so you can do it that way, but I could be wrong. I don't know. So maybe it was a fancy one, so. All right, so don't forget, test tomorrow, 131 barrows or You're gonna be doing it remotely? Just make sure you let me know. I will see you tomorrow, bright and early, 9 AM.
But, yeah.
I think it's 6.
They just.
Yes. All right, take care, y'all.